Hello and welcome to the Embedded C Programming Design Patterns course. This course is available here on YouTube, and also if you don't want to wait until the next module comes out, you can get this course as a book, as book plus videos, Udemy course, and also all of the book and video content, as well as live sessions with me on Wednesdays, which is available at swedishembedded.com. So the book is available on Kindle. You can download it from Amazon. The Udemy course contains the book materials as resources, as PDFs here. And on the website, we have the course available as a standalone course directly on the website. You just click join here, enter your details, register as a student, and then you will have access to all the course materials and also the weekly Q&A, which is in 5 days, 8 hours at the time when I'm recording this. All right, so let's get on with the next module of this course. Hello and welcome to another module of the Swedish Embedded Design Patterns training. My name is Martin Schroeder at swedishembedded.com. If you have any questions regarding this training, I suggest you join our Discord channel. It is available at swedishembedded.com. And if you fail to join the Discord channel or you just want to contact me directly, you can always email me at martin.schroeder@swedishembedded.com. In this module, we're going to look at the virtual API pattern, which is the primary way of implementing virtual functions in C. So in other languages such as C++, we have language constructs that allow us to override methods and implement interfaces. But in C, we don't really have inheritance built into the language, but we do have a way of implementing polymorphism, and that is what this pattern is all about. So in this module, we're going to look at how we can implement interfaces and expand a little bit on the concept of traits, which we discussed earlier, and make sure that we can implement this in a type-safe and memory-efficient way. So what are some defining characteristics of this pattern? Well, basically this is a trait pattern, but the only difference is that we are keeping the trait object constant, and we're keeping pointer to that trait object inside of our instances. Now this does have a little drawback that we cannot have different APIs for different instances of the same object, but on the other hand, in embedded systems, we don't usually do that. Instead, we set things up at compile time, and then we just use our objects interchangeably. So the primary use of this pattern is actually to organize groups of objects that have different implementation, but that behave the same way. And this basically helps us to achieve memory efficiency, and we can still make full use of the indirect functions that we can access through through the trait objects. Anyway, I'm going to explain this in more detail when you look at an example, so it's going to be easier to understand. Some of the main use cases of this pattern, and by the way, this pattern is useful in any place where you need to treat objects the same way, but you have different implementations. And in embedded systems, the most common use cases for this pattern are the device drivers. So device drivers are a typical use case because we can have multiple implementations of the same functionality. So for example, if you just take something as simple as a UART, it's going to have many different implementations depending on the hardware, but the basic functionality is always the same. So we define our interface, we standardize the interface to all UARTs, and then we have multiple implementations that implement the UART functionality on the different types of hardware. And that's exactly what the virtual API pattern is all about. We're creating an API, which is generic, and then we create multiple implementations, and we can then use the same API everywhere, regardless of the implementation. So the implementation is effectively hidden, and we can treat all of the objects just the same. Number two is plugins. So if you basically, this is like an extension to the device driver pattern, where a device driver is essentially a plugin for a particular type of hardware that we add to the system. But plugins are a use case for this pattern that expands the scope of how we can use this pattern. So we can have, for example, a dynamic library that we load into our application, and we then call one particular method, like we create a specific method just to get the interface for that library, and the dynamic library exports essentially a virtual API interface. So it gives this handle to the application, and then the application can treat all of the plugins just the same. So it's another example of this abstract API pattern. And number 3 is abstract data types. So let's say we want to have multiple data types that have the same behaviors, and we want to be able to treat those data types. We want to be able to make operations on those data types generically without having to know exactly what type we are dealing with. And that's also a use case for the abstract API pattern, because we can have multiple data types that essentially implement the same interface. So the question becomes, what abstract interface does our data type implement? And then if it does implement that interface, we can get a handle to that interface, and we can then treat this data type according to the behavior of that interface. So we can make assumptions about it. Some of the benefits we get with abstract APIs is that we achieve decoupling. So we have the implementations completely decoupled from the rest of the application. We don't care about the particular implementations. We just care about the implementation following the requirements of the interface and implementing those requirements. So we have this decoupling between the actual implementation and the rest of the code. We get type safety with this particular pattern. So there are other ways of implementing virtual functions in C, but with this pattern that I'm about to show you here, you get type safety. So you get full type safety, in fact. We are not using any void pointers anywhere. We are not casting any objects in ways that are not predictable. So we can never end up with a situation where we get the wrong type of object, and maybe we never get into the situation where we can cast one object to a wrong type. So this is very good in terms of the safety of this pattern. And number 3 is opaque handles. So every single interface that we deal with, that we pass around in the application, is completely opaque. We don't have any knowledge of the internal data structures of those particular objects, and that's by design, because we shouldn't need to care about the actual implementation of the object. We just care about the functionality that it provides to us. And with this, we do get some drawbacks. So number 1 is complexity, because we add additional functions that are designed to sort of implement our interface. And we also have to code our objects in a particular way. So we need to, first of all, we need to define our list of functions that we implement from the interface. We need to implement those functions. We need to follow a particular pattern when implementing those functions. For example, they all need to be static, and they all need to retrieve the self pointer through the container of macro. We might also get into the inflexibility, because we're trying here to implement a generic interface. And this is one of the requirements for the pattern, because we don't want to have a lot of implementation specific information in the interface. In fact, we don't want any of that information at all. So we're trying to come up with a generic interface that works for all types of implementations. But sometimes this can be hard, because maybe you have some very implementation specific functionality that still needs specific support from the implementation. So we either need to find ways around it, or we need to split our interface into 2 different interfaces, where one is the normal one and the other one is maybe the extended one or something else. So it can result in a kind of inflexibility, because we're also limited to just functions that we can call, the operations that we can do on the interface. We don't have any data embedded in the interface either. And lastly, there's a slight performance overhead, because we're always calling those functions through dereferencing a data structure, a pointer. Normally, this is a very minor performance overhead, and some people think that it is a significant overhead. But if you think of it in terms of how many operations you're going to be doing in the implementation, compared to that, this is very minor and very tiny overhead that almost doesn't make any sense to worry about. But nonetheless, there's still an overhead, and there's also an overhead in terms of coding those functions, because you have to implement the function, you have to assign it in the table of pointers, you need to register those with some kind of singleton manager that manages all of the implementations that can allows the application to query one of the pointers. So for example, as we have in Zephyr, we can call device get binding, and we can get a generic pointer to a particular device, but we still need to have a lot of code around that to query those things and to manage the generic pointers. So a little bit more complexity, can be a little bit inflexible, and can have a certain performance overhead. Let's now go right into the implementation. So we're going to have three parts of the implementation. We're going to have the generic API, which operates on generic handles. We're going to have the API interface itself, which is our trait definition. And we're going to have the actual implementation of the interface. So let's look at how we actually implement this in C. So we're going to start off by defining the trait itself. And in this case, we're going to work with a serial interface. So a serial interface would have obviously more functions than read and write, but in this case, let's just assume that the serial interface must have read and write functionality. And when you're designing the abstract API, you should ask yourself, okay, so what should all of the possible serial interfaces always provide? And that's going to be your trait definition. So you're going to define a data structure. In this case, we call it serial ops. And you can also then type def this data structure or a pointer to pointer to a const pointer to pointer to serial ops as serial t. And the reason it kind of makes sense to do this type def, usually we don't type def things, but in this case, we can type def this because we're going to be using this a lot. So this pointer to pointer is going to be passed to all of the callbacks of our interface. And the reason this is pointer to pointer is because we're going to be passing a pointer to another pointer which is contained in our implementation. I'll explain why we do that as well. So the next step is to implement the generic trait API. And this API is going to operate on the handles, which are pointers to serial ops in this case. And this is a generic API. So in this case, we implement methods such as serial write and serial read. And these methods will be used for all implementations of serial interfaces. So regardless of which serial interface we use, we always would just retrieve the handle to that interface, and then we would use the generic methods everywhere. So these methods are the ones we're going to use throughout our application. And the reason we implement these methods is because we want to really avoid doing this everywhere in our application. So these methods are just wrappers around the handle, which dereferences the handle and then passes the handle to the function pointer that is defined as part of the data structure we defined here. So we're going to assign these methods at compile time inside our implementation. So then we can move on to the implementation header. So basically, this was our generic trait API. And lastly, we will look at the implementation itself. So in the implementation, we would have our particular or specific data structure. In this case, we call it serial impl. But this would typically be, if this were a real serial interface, this would be, for example, STM32 serial interface. And this interface would contain a pointer to the serial ops data structure. So a const pointer construct serial ops pointer serial. And we would then have methods that are specific to this implementation, so private to the implementation. And we can also implement the method to cast from our particular data type to a serial handle. So we can have serial underscore t here, and then serial impl to serial would just give us the handle that we can then use with the generic functions. And when it comes to implementation of these, we have our serial ops data structure here. We declare it as static const. We assign this at compile time. And then in our implementation, we set our pointer to this interface inside our specific data structure. And so this is the reason. So here we also have this casting operation, which gets the pointer to this pointer. So the pointer to the serial serial member of the serial impl structure. And this is the pointer we're going to be passing around. But the reason we do this is because we want to be able to get also the pointer to our serial impl. So this should actually be serial impl here, using container off. So we can then call container off on the handle, and we tell it that this handle is pointing to member called serial inside the struct serial impl. And so we get a pointer to struct serial impl here, self. And then we can operate on our actual implementation specific data structure and do whatever is needed to kind of read and write data to the serial port. So that's it. And these functions are always static. They have the same signature as the methods that we have inside our serial ops. And it is the serial ops that defines the generic operations that we can do on our serial interfaces. So anything that we put there must be generic enough so that it's going to be implemented for every single serial implementation. And that's one of the drawbacks here, is that if you you really cannot include any implementation specific stuff into this generic interface, because then you would have to force all of the implementations to basically implement that functionality as well. So we try to keep this functionality as generic as possible and just provide this generic, very lightweight generic interface so that the application can then start using the serial port. But the application doesn't need to know about the initialization of the serial port, about any specifics of how data is transmitted. It just needs to provide this generic interface. And then when it comes time to use this, basically in a very simple scenario, we can just instantiate our implementation. We can get the handle to our generic serial interface, and then we can call serial write, for example, on this generic handle. And this is how you would typically use it in the application. Now, there is also a possibility to add like a manager for all of the device drivers, for example, where each device driver can then register this generic handle. So we don't need to instantiate anything. We don't need to actually know about any specific implementation. We would just query a handle based on, let's say, device tree label, or based on some kind of string definition or a name. So in this way, we can achieve very high degree of generality in our C code. Even though C doesn't support virtual functions through the language, we can kind of implement the philosophy of virtual functions and implement the philosophy of polymorphism in C using this virtual API pattern. Let's look at some of the best practices when implementing this pattern. And number one is that trait operations must be thoroughly defined. So every implementation must follow clear implementation guidelines. So you need to have, you need to really think through this generic interface, because if you don't do it, any changes you make to it later would require you to make many different other changes in all of the implementations that use it. So this becomes kind of, the virtual interface becomes the central point where you need to define the behaviors very clearly so that all of the implementations can then follow the same definition and that you don't change this definition later. Number two is that you can type def the handle for simplicity. And number three is that you should really keep the traits constant. So even though we could implement a way of kind of reassigning the functions at runtime, we don't usually do that in C because it just complicates things and it makes things less predictable. When we implement this kind of polymorphism in C, we don't really make any changes to the assignments of the functions after the program has been compiled. And that's also a safety feature where you could actually place those data structures that are constant into read-only data memory, and then you can avoid any possibility that some bug or something else in the code overwrites these function pointers, which would obviously mess things up for you. And by making them constant, we improve the safety of our application, especially because we're working with embedded systems. We need to really keep that in mind. And the most common pitfalls of using polymorphism in this way is that you might run into the situation where you overuse the abstract interfaces. And when you have a lot of abstract interfaces, then something is really wrong. You should have abstract interfaces only for very well-defined classes of objects. For example, in an embedded system, you might have a serial interface, you might have a SPI interface, so serial would be corresponding basically to UART. You can have an SPI, you can have an I2C. Those classes of objects would have a lot of different implementations depending on the hardware you're running on. So there it makes sense to have abstract interfaces. But then you might run into a situation where you really start using abstract interfaces for almost everything. And when you see that you need to make changes to your abstract interfaces, that's a good indication that you're using this in the wrong way. Because if you're doing it right, you should be able to define the abstract interface once, and then you would just maybe add some new methods to it. But for the most part, it's going to stay the same for the duration of your project. Number 2 is insufficient testing, because if you change any requirements on the abstract interface, you need to have tests in place that can discover that some of the code, some of the implementation code that already exists in the project doesn't does follow the new requirements. So you need to have a way of discovering inconsistencies in implementations compared to the requiremတဲ့that the abstract interface defines. And if you don't have tests in place, you might get implementations that come out of sync with the requirements of the interface. So then you will be using the interface in one way, expecting one thing, and the implementation would just behave differently. And that would basically complicate things during development. So you need to have sufficient testing in place that can discover any inconsistencies between the implementations and the interface. The abstract interface itself. Overly specific interfaces. This is a pitfall that occurs if you try to use abstract interfaces for everything, and inconsistent implementations of a virtual API pattern. So there's multiple ways you can implement this. And for example, in Zephyr, you have the generic device structure, and it has kind of a generic API, which is then cast to a specific API when you call the API functions. And if you try to kind of, if you go outside of the way that I just shown you of how to implement this pattern, you would get inconsistent implementation. So you would be doing it differently in every place. And I've created this pattern specifically to accommodate for all of the common requirements of this of polymorphism when you try to implement it in C. So the pattern that I just shown you is memory efficient, it's type safe, and it's basically very easy to work with. So anything else that you are likely to come up with is probably going to be worse than what you've just seen. So it's really important that you just follow this pattern exactly as I shown you, because it has been optimized for this kind of thing. And in C, we are really limited in terms of how we can implement those things. So the pattern is probably the best one that you'll ever find anywhere. There are two main alternatives to this pattern. We have the callback pattern, which is a simpler implementation of the traits objects, but the callback pattern is kind of backwards in terms of how it works. So with the callback pattern, we can separate the we can make the callback caller independent of the callback listeners. But with a virtual API pattern, we make the actual listener or the implementation independent of the caller. And the second alternative is the event bus pattern. The event bus separates both the listener and the emitter of an event, and it basically transfers all of the parameters as data through events which can be subscribed to by multiple listeners. And you can have also multiple event emitters publishing to the same topics that other listeners subscribe to. So it's a more flexible pattern and also more complicated to implement. So in this module, you learned generic virtual API in C, polymorphism, the way that we can implement it in C. We have kind of doubled down on traits, the trait objects. That concept is rather new. You wouldn't hear others talking about it, but I think it's a much easier way to understand what we're trying to do if we treat those data structures with function pointers as traits, as ways of describing certain features of a collection of objects. And we looked at generic, type-safe, memory-efficient implementation of this pattern. So now let's look at your understanding of this pattern. So how does the virtual API pattern differ from the trait objects that we described in the inheritance pattern? How does defining our API handles as pointer to pointer help us stay memory efficient? Why are we doing that in the first place? Why is it so important that the virtual API itself does not contain any implementation-specific details at all? What are we actually trying to do here? Why is it important that it's generic? What would be the consequences if it's not generic? Why do we need to have a generic API alongside of our trait objects? Why do we have to implement the wrappers? What is the reason why we have this generic API wrappers that we use as helpers then to call the virtual methods? All right, I hope you learned something, and I hope you can use this pattern in your embedded projects, and I'll see you in the next module. Bye for now.